All right, two sketches, and one of them is polynomial, and one of them is rational. And again, this is, yesterday we talked about concavity. Not concavity, it's concavity. So this and second derivatives, and so that's what both of these sketches are going to sort of highlight and involve. That we're finding points of inflection and doing the whole show, and we've got everything. Okay, so this one is polynomial. Complete a fully labeled sketch, given function showing all intercepts, asymptotes, critical points, and points of inflection. First thing I'm going to do is factor this thing. If you know the steps and you want to start working ahead, I think that's a great idea. Okay, I can't factor any numbers out, so I'm factoring out x cubed. Then what? It is a tricky trinomial. So what do we do? Factor it. But it's not factorable. So factor or? Quadratic formula. So it will be the quadratic formula. I'm going to do that after. But if you check b squared minus 4ac, check the discriminant, always a good thing. And you'll find out that one's not factorable. So next I'm going to take its derivative. I can't stress this enough. I said this yesterday. I'm going to repeat it again. This seems easy when somebody's walking you through it. It's not easy. It seems obvious which one we're going to take the derivative of. It's not obvious. When you're doing this on your own and you're in the middle of a test and you're worried about timing and you're starting to rush or panic or whatever, okay? So the more practice you do so that you make sure you can do this independently, better off you're going to be. You want to know as quickly as possible which version is easiest to take the derivative of. And for polynomial functions like this, it's always the expanded, simplified version that's easiest. So I'm going to take the derivative of that one, 10x to the fourth minus 20x cubed minus 30x squared. And we're going to factor it. And this trinomial is factorable. Okay, and now that one's done. Okay, and then we're going to factor it again. Imagine you tried to factor with this last line. That would be the extended product rule for derivatives, right? The PQR thing that we did very briefly that day. So, oh my gosh, that would be ridiculous to do that when it's so easy to do it when it's in its expanded form. So this looks like 40x cubed minus 60x squared minus 60x. Factor that. I'm going to b squared minus 4ac this. So that's 9 plus 4 times 2 times 3. 33. Again, this, so not factorable, but yeah, it's solvable. So you're going to use the quadratic formula. That's a really important thing to note. Some people get to this point, it's not factorable, so they say, so there's no solutions. So then you think there are no POIs, because that's what the second derivative gives us. No changes in concavity. Same thing with this one. People say, oh, there are no x-intercepts. That doesn't make any sense. This is degree 5. It's got to have at least one x-intercept. Well, I guess it's got that one. It's got 0, so never mind. I guess that could qualify. But this thing will have other x-intercepts. So if you thought that it wasn't even solvable, that's different from not factorable. So be careful.
So if it was negative 33, does that make it not solvable?
Exactly. If b squared minus 4ac is a negative, then it's not solvable. What does that mean? It means the function has no POIs. It doesn't change in concavity. Okay, and that's possible, but probably not for a question where we're making you do the second derivative. There's probably going to be POIs for you to find. Okay. I like to do all this derivative and cleaning up and stuff like that, so I've got it. So when I start doing the other stuff, I can just pick out which version of this I want to use, and I don't have to go and do any other algebra. That's my preference. Okay, but you got to come up with a system that works for you. And like I said before, it is beneficial to come up with habits and do it the same thing every time. Intercepts. Y-intercept is 0. So x-intercept is also 0. And my other x-intercepts are 5 plus minus square root of 105 over 4. Which are negative 1.3 and 3.8. Mm-hmm.
You don't have to show any of the quadratic formula.
No, gosh, no. I would do it like this, though. I would write the exact value, sort of simplified like that, and then the decimal value. Okay. Okay. Then asymptotes. So what's the deal with asymptotes? There are none. It's polynomial. Critical value is when the first derivative is equal to 0 or does not exist. It exists for all x. Where does it equal 0? So that's my factored form of the first derivative, which is right up here at the top. So at negative 1, 0, and positive 3. For possible points of inflection, this is when f double prime, our second derivative, does not exist or is equal to 0. It exists everywhere. Where is it equal to 0? So I'm going back up to my second derivative at 0. And remember, that has solutions. So it might have up to 3 points of inflection. So at 0, and then the other one is 3 plus minus square root of 33. That was the one that I checked, right? Over 4, which is negative 0.7 and 2.2. There's a lot going on at 0. This happens sometimes. The trig ones, there's a lot happening at pi by 2 or something like that. right? There'll be one place where there's a whole bunch of things happening. I got an x-intercept, so the y-intercept as well. I have a critical value there, so a turning point or something, and possibly a point of inflection. A lot going on at 0. Now what do we do? Yes, and we're doing a second derivative chart, which is required for intervals of concavity. All right, x less than negative 0.7. Negative 0.7. Negative 0.7 less than x less than 0. 0. 0 less than x less than 2.2. 2.2. X greater than 2.2. I got a lot of points to find, and I got a lot of testing to do. This testing actually, no, it's not going to be easy, is it? Testing in that thing's not going to be easy. So you may very well choose, it'd be a good idea to program that into your calculator. Okay? Then you're going to have to type it out by hand, or get a new calculator, or like if you just practice with one of mine, I have lots of one you can borrow. Right, I've always got lots in here, so you can borrow one of mine, but you'll have to learn how to use it ahead of time. But it's probably worthwhile. So I'm punching something that is big negative, negative 10 or something, into the second derivative, and I'm going to do these for us to save time, so you're not going to have time to do them all yourself. This first one works out to be negative. So concave down, then 0, then positive, then 0, then negative, then 0, then positive. So this one does flip back and forth, but they don't necessarily always do that. So take a look. This is when you make your conclusion. It changed from concave down to concave up. Therefore, this is a POI. That's how we draw that conclusion. Point of inflection is where it changes concavity. So it changed concavity at this point. So this is a POI. Whoops, concave down, concave up. So again, all of these, turns out, are POIs.
I didn't do yesterday's homework, but when you find a critical point for like the first derivative and the tangent line is 0, so wherever that x-intercept for the first derivative is, and let's say it's concave down, does that mean that that would be a local maximum?
Right.
So that's how we classify this.
It's how you classify it. You think about the interval that the critical point is in, and if it's an interval that's concave down, then it's got to be a turning point with a maximum. And if it's an interval that's concave up, then it's got to be a turning point with a minimum.
And that's basically yesterday's homework.
That was a part of learning how to do all of this, yeah. Like, that's one of the things that new things we need to learn when we're doing this work with the second derivative chart, but still classifying critical values. Yeah. No? Okay. Okay, so now we are going to slot these in. So I've got critical values at -1, 0, and 3. So -1 is in this concave down region, or interval. So, like we just talked about, this is a turning point max at -1. So now I'm punching this into the original equation to get the y value. Turns out it's a nice one. It's just 3. I also need this POI, which is -0.7. Punch that in. Turns out it's at 1.8. Where's my next critical value? If I'm doing them in order from left to right. At 0. So that's at this POI. And that's 0, 0. We already know that point. But what is it? What does it mean to change concavity? What does it look like from being concave up? Like, draw it on scrap paper on the back or something. Concave up, changing to concave down, and it's also a critical value. So what is it? Nasir, do you know? It's a horizontal twist because I'm concave up and then I'm concave down. Now, all points of inflection don't look like this. Okay, sometimes they're very subtle. We saw that in the little diagrams we had on the handout yesterday. But this one does look like that. And you can convince yourself of this. That will always happen. If you have a critical point on a point of inflection, it's a horizontal tangent line. Because how could it be a turning point? Yep.
Would that be on a test thing?
No. Okay, so this is a horizontal tangent line, which means it's a horizontal twist. And it's at 0, 0. We already know that point. My next one is 3, so it comes down here in a concave up region. So now I have my next POI is at 2.2, and punching that into my equation, it's at -118.8. And then this one is a turning point. It's concave up, so it's a turning point with a minimum. Yes?
Why do you just like choosing these random like things and just like okay, we're gonna put this in and get that value?
Say that again?
Okay, so now for the start, you got turning point max for concave down.
Yep.
But now there's a concave up right afterwards.
Yep.
Why would you do anything with that?
Because we didn't find a critical value in that interval. So I'm taking these from right here.
Oh, okay.
Right? Those are my critical values. So I'm slotting those in as well as finding what the points of inflection are. Like, I'm finding all the y values and I'm just organizing it in this table. And at the same time, like, maybe I should have done that in a different order. Just do the POIs, have them done, and then slot in my 3 critical values, classify them, determine what they are based on what region they're in, that kind of thing. And find them as points as well. So I did all of that all together. So we got A, B, C, D, E. 5 things going on. Plus other intercepts. And, after you do this, maybe you take a second and you just say, have I done everything? Like, did I actually do the derivatives, or did I just make this up? Did I get my intercepts? Did I do my asymptotes? Have I missed anything before you start actually graphing? Might not be a bad idea to make sure that you don't get partway through the graph and realize you missed something and you've wasted a whole bunch of time starting to build a graph that can't exist or that's missing something and you have to start all over again. Now, because I've graphed this before, I happen to know that there's a lot of labels that are going to be really close together, so I'm going to kind of spread them out a little bit. You wouldn't know this on a test, as long as it's readable, that's good enough. But like if you gotta get little numbers in there or something, make sure your pencil's sharp. That is all I could recommend. Don't be doing this in pen, making a mistake, having to scratch it out and write it somewhere else. Like that would be a bad idea, right? So obviously, I don't expect the same level of perfection when it's your first time going through a graph and you don't know what it's going to look like yet and how tight things are going to be. But it is something that you have to consider as you go. So I'm starting from the left here, and my first interesting thing that happens is an x-intercept, and it's at negative 1.3. Then I'm going to have a point there. And I'm going to have another intercept. I'm going to wait and label that one after. It's going to be over here somewhere. It's at 3.8. I've got a turning point max somewhere around here. Okay, so I'm going to start drawing. Now, something else happens here. When I'm drawing these, just watch for a minute. I think to myself, what kind of concavity am I drawing? When does it switch to the next kind? Because I'm going to do that. I'm going to do this quickly, and then like I'm coming around, and then I'm switching to go like that, right? I don't go back up, but like, right? So somewhere right in here, I switched from being concave down to concave up. Do you understand what I'm saying? I kind of think about that as I'm drawing it. I just think it's a good reflection to make, but then you also can pinpoint your point of inflection a little bit better. So I'm coming around, I'm concave down and concave down, now I'm concave up. And I'm coming down and I hit this. Switching back to concave down, this is a horizontal twist. Okay. Then this goes really, really far down. That was not good. Concave down, concave down. Oh, now I'm concave up again. See how subtle that was? That is not a horizontal twist. But I just changed in this little interval from concave down to concave up. I kind of felt it as I was drawing it. I don't know that this is necessary, but I think it's useful. And the reason why is because now I got to curve up, right? To have that local minimum, the turning point with a min, and come back up to have my other intercept. So I'm going to go back in and label some things. So I was concave down to right about here, concave up. This is the intercept of 3.8. This is a turning point with a minimum. And I'm going to go label all of these values. That should probably be way lower. Obviously, my y-axis is not going to be drawn to scale, and that's fine. Because this point, that doesn't make any sense. It's like a logarithmic scale right there. And this, and this. And where did I change? Right around here. So see how you got a whole bunch of things crammed into a tiny little space right in this area. So this is -1 and 3. This is negative 0.7 and 1.8. This is 2.2. See, even that's not very well. And negative 118.8. And this is negative 189 and 3. A, B, C, D, E. Any questions about that one? Yeah.
So you don't really care, like, you know how that negative 1.3 is like where negative 3 would really be?
Yeah,
Like,
no.
you don't really care about that.
No. Do your best. I like to try to, but it's more important that it's readable. And because of the difference between the maximum of 3 and the minimum of negative 189, like you can't hardly draw that to scale. It wouldn't look like a polynomial. It would look funnier if you drew it that way, but I mean it wouldn't be wrong, just as long as it's labeled correctly.
Do you want us like to label it like points of interest or?
Yeah. Yeah, points of inflection and critical values, critical points labeled. The way I do A, B, C, D? Yeah. Like, or as an ordered pair. Some people do it as an ordered pair. I don't really remember that. When we do sketches, I always label them A, B, C, D. If you, like, at the very least, you have to have this labeled. Not every teacher has A, B, C, D, but you got to have your points labeled. I like to line them up with the table as well. But okay, one more. Same instructions, complete a fully labeled sketch of y equals f at x, given the function below showing all intercepts, asymptotes, critical points, and points of inflection. I'm going to expand the bottom. Remember we talked about sometimes you want to do this, sometimes it's useful, sometimes maybe it's not so useful for finding the y-intercept. In this case, it looks like it's not useful, but I'm doing it anyway. So we'll see what happens later. Okay, and now I'm going to take the derivative. Don't be fooled. This is quotient rule. Oh my goodness. People do that part wrong. Don't even do quotient rule. And nothing's going to make sense. Okay, so derivative of the top times the bottom minus derivative of the bottom times the top. Over the bottom squared. Start cleaning this up so I can common factor an x squared and an x minus 1. And I'm left with 3x minus 1 minus 2x. Oops, not cubed yet to the fourth, but it's going to divide out. So this is 3x minus 3 minus 2x. Okay. Here's a new trick. I'm going to expand the top. Why? In grade 11, the very first unit of the course is rational expressions. And you do all this factoring, a crazy amount of factoring. If you don't learn to factor in grade 10, you really struggle in grade 11 university. In that very first week of class, crazy, right? And it's a hard unit because you don't know when you're supposed to expand, when you're supposed to factor, how am I supposed to be doing this? When am I supposed to be doing this? And for people who don't understand why you're doing what you're doing, it just looks random. Why are we sometimes expanding and sometimes factoring? I don't get it. And that could happen in this unit as well. Like, why did I just expand that? Why would I bother? I don't think we used to do that. It gets rid of product rule on top if I was doing, that's what you meant. Yeah, I know. Very good. If I didn't do that last step and I was doing the derivative, I'd have product rule inside quotient rule. Yuck. Okay, not going to be good at all. So again, this is pretty necessary in this case because we're taking its derivative again. Would I have to do that to the second derivative? I don't see why I would. I don't see what value that would add. All right. On that note, let's do second derivative. So the derivative of the top, and I'm using that last line that I just expanded like I just talked about, is 3x squared minus 6x times the bottom minus derivative of the bottom bring the 3 down, x minus 1 squared, and then times the derivative of what's inside. But in this case, that's just 1, so I'm not bothering with it, right? But if this was 2x minus 1, which it absolutely could be, then you'd have to also do the derivative of what's inside and include that in your derivative. Okay, times the top. Over the bottom squared. Next step can be done however you like, but the fewer steps you can do it in, the more efficient you're going to be. That's a good thing. So I'm going to do it in one step, and I'm looking inside this, and I see that there's a common factor of 3 and a common factor of x, and take a look at the other thing. It's got a 3 in it, and it's got a common factor of x. So I've got 3x in both. But because they're not isolated together, it might not look like that. You might not recognize that you've got both those things. The 3 could be factored out later maybe, but the x, you want to factor it out now. How else would you recognize that? I mean, I guess you would common factor both of them individually, common factor them fully, and then see that there's something common in the common factors. Like, I guess that's how you do it. So you do it in a couple of steps, but it's better to do it all at once. And then I've also got an x minus 1 squared. That's common between both of them. And then what's left in here is x minus 2. So 3x squared dividing out 3x leaves me with x, and negative 6x dividing out 3x leaves me with 2, and an x minus 1. Minus, the 3's gone, the x minus 1 squared's gone, so I've got common factored, an x out of that. These two divide with this. Okay, so I'm expanding. Yes?
Why is that a minus 3x at the end there
This?
yeah, because the x minus 2, you end up taking a 3 out there, so
So this 3 that I common factored out
it can only go that way.
is this. You see it okay? And the x that common factored there, see how should be an x. Okay. Look what happens here. X squared minus x squared gone. Negative 3x plus 3x gone. Doesn't always work out this way. Every question's a little different. 3x times 2 is 6x over x minus 1 to the 4th. Whew. Simplified nicer than the first derivative.
One question. Why don't you guys just teach us how to take a derivative again in Gaussian?
We have done that. Taking the derivative again is just taking the derivative again. If you're not doing anything with it, it's not different than the first time around. So I think we just think it doesn't really add any extra value in terms of your skill level in doing it. And when we used to do it in the context of position, speed, and acceleration, like we were talking about yesterday at the end of class. And but it's, I don't know, it wasn't a very good use of a day. We didn't find, so we kind of cut it until it has some relevance. Okay, and that one's done. Do you have any idea how hard these are to come up with, like nice ones like this that work out? Like, I don't think you really understand how amazing that is. Yeah, thank you very much. It's not an easy thing to do, okay? All right. A little applause once in a while would go a long way. Yeah, okay, no. It was a joke, okay. Okay, so we've got our derivatives. We've got them all cleaned up. I think we've kind of got every form that we want. So now we're going to start doing intercepts, asymptotes, critical values, possible points of inflection, second derivative chart, put it all together into a graph. Like nothing, right? It's like, yeah. All right, intercepts. Well, that's going to be easy. My y-intercept is 0 and my x-intercept is 0. That's it. Asymptotes. Do we have any asymptotes? Yes, we do. Okay, so a vertical asymptote at x equals 1, very nice. So the limit as x approaches 1 from the left of f at x, and the limit as x approaches 1 from the right of f at x. So if I'm just to the left of 1, oh, the bottom's always positive, right? Bottom's always positive. So I'm putting something positive into x cubed, it's going to be positive. On the other side of 1, I'm putting something positive into x cubed, it's still positive. So both of these are going to be positive infinity. Now, somebody tell me something else about this. It's an oblique asymptote. So how do we find an oblique asymptote? Sarah? You have to divide. Somebody tell me something about how I'm going to divide this thing this year. Long division. I don't want to use long division. I don't like it. I want to use synthetic. Why are you telling me to use long division? You were about to tell me why I have to use long division.
You don't. You just do x minus 1 twice, right? You just divide by x minus 1.
No. You have to use long division.
Oh.
Huh? Kind of. More because of what I'm dividing by, which is degree 2.
Just do x minus divide x degree by x minus 1 over and over again twice. Isn't that the same thing? Using synthetic.
Try it. Yeah, might work. I'm going to use long division.
Doesn't that take so long?
What? Long division?
It's the whole process of everything.
Yeah, like how are
Yeah.
we supposed to do that?
That's why I need to keep going. We're going to run out of time here. Okay, so x squared.
This is one of the second test.
Also, that won't always work because it might not be factorable, right? So you can always do that. And so, like, I want to review it. We haven't done long division in a long time, so I also just want to review long division. So we've got x cubed. Oh, the top is just x cubed. So would I just leave it like that?
No.
What do I need? Good. Okay. Well, maybe we don't need to review this. Everybody's on the ball. I love it. Okay. S squared goes into x times. Subtract. Bring down the 0. What am I left with? 0, 3x minus 2. Okay, and then you have to write it out like that. And split it up into the oblique asymptote, which is y equals x plus 2, and the remainder part. Okay, so I've got my oblique asymptote. I've got its equation, which is important. It's really crucial that you get its intercepts correctly and you understand what's going on with that. And then I got my remainder. I'm going to do the testing. I'm going to speed up a little bit here. Oops. Oh, -2. This is negative. This is positive. Below and above. Still see that okay? For critical values, so I'm going to skip over a few things here because we've talked about it already. F prime at x does not exist at x equals 1. That's from the first derivative, obviously, but that's a vertical asymptote, so it's not a critical point. But we still need to include it in our chart. Well, we're not doing a first derivative chart, but. And then this one factored, so I'm going back to factored form, and I can see that it has 2 critical values, at 0 and at 3. And again, the second derivative does not exist at x equals 1, but again, that's just our vertical asymptote. It's redundant, but you got to say it every time to make sure that we're complete. And then this one has 1 possible point of inflection at x equals 0. Okay, second derivative chart. Less than 0, 0, 0, less than x, less than 1, 1, x greater than 1. It's a smaller one than the last few that we've seen, I feel like. And in this case, actually, the testing's pretty easy, because take a look at our second derivative. It's 6x over x minus 1 all to the fourth. X minus 1 to the fourth is always going to be positive. So it just depends on the 6x. And that's easy. If I'm less than 0, I'm negative. It's going to be negative. If I'm greater than 0, between 0 and 1 or greater than 1, 6 times a positive is positive. So both of these are positives. So it was negative, then it was 0, and then this is where it does not exist because it's a vertical asymptote. So this is concave down, this is concave up, and this is concave up. Because it switched, this is a POI. So we got a POI that is also a critical value. So this is again a horizontal tangent line with a horizontal twist at 0, 0. And I have my other critical value was at 3, which is in this bottom interval. And that's a concave up region. So this is a turning point with a minimum. And it's at 3, 6.75. Okay, let me quickly do this. And then if there's any questions or if you need to catch up on anything that you missed, you can do that. Oops. Nope, that's not what I want. Ruler. Remember with these oblique asymptotes, you want them to be leaning less steep than you might imagine. If you make it too steep, you might not be able to draw the graph. It has to cross all of the vertical asymptotes. Okay, so I've got an easy region in here because it's going up as it approaches from the right. Comes down, it's got a local minimum, turning point with a minimum, and then it approaches the other one from above. But what does this one do? This one starts up here. It's going up as it approaches from the left. It's going to come down, and it's concave up in this region. It's going to twist and go to concave down and approach the other asymptote from below. So it's going to go like this. And from here, it's really kind of hard to draw, but it's like look at that. It's concave down, approaching the asymptote from below. Like that's a kind of a tricky thing that's happening, right? But that is exactly what's happening. So that's my point A at 0, 0. This is my point B. And point B is occurring at 6.75 and 3. Did I miss anything? I think I'm good. I didn't label my oblique asymptote. Okay, now I'm good.